Okay, one quick note related to system of particles. I think it is important to mention this and be explicit about it. So I mentioned principle of work and energy, T1 plus total U from 1 to 2 gives you T2, final kinetic energy. This always works. But when you have a system of particles, you can imagine there are a whole bunch of internal forces that are shown with green and a bunch of external forces acting on the system. To really work out this equation, what you can do is calculate the entire kinetic energies at the beginning, kinetic energy of all particles at the beginning, and calculate all works done by all forces, including both internal and external. That will give you the final kinetic energy of the entire system. So these summations are over the entire particle, all particles in your system. And the summation for work is the summation over all forces, including internal and external. I can actually go and expand this. T1 plus, I can separate these. All the internal works, all the external works, that should give you the total kinetic energy at the end. But one thing to note here, when we were talking about Newton's equations, we said internal forces, we can ignore them. Yes, because for any force from particle 1 to particle 2, there is an exact opposite force from 2 to 1, and the sum of internal forces would cancel out. But that is not the case with the energy. Note that if you have a flexible object, the distance between different particles may change, and these internal forces may do some work, and if the forces are not conservative, they may actually decrease the energy of your system. And you see that quite often. Imagine you have a rubber band. Feel free to do this at home if you have a rubber band around you. As you cyclically stretch the band, do it many times fast, you will notice that the rubber band heats up. And that is because of all these internal forces. There is some kind of dissipative effect to these internal forces, and they turn into heat. And if you, doesn't really work with rubber band. Yeah, it does. If you hang a mass from it and pull the mass down and let it go, it oscillates, but eventually stops. Your oscillator stops because these internal dissipative forces eventually eat into the energy of the system. That is, so in long story short, for work and energy principle, you cannot ignore the internal forces. Their work may be dissipative, usually dissipative, and change the energy of your system. However, if all these internal forces are due, for instance, to conservative factors, in that case, all these internal forces become, because they are non-conservative, they don't change the energy of your system. And then you can write all the potential energies all kinetic energies of all particles plus all the potential energies due to these elastic or could be gravitational This should equal to final kinetic and final potential energies. Let me make a bit of a space. If all internal forces are conservative. Well, actually, let me make it even nicer. So if you start with some total mechanical energy of the entire system, you may actually, it's fine, let's add this. All the external ones, that should give you total energy, total mechanical energy at a later time. So in that case, essentially, if you notice, the difference of these two give me the change in the internal potential energy of the system. Okay, that's all I wanted to say. That be careful about internal forces. They may very well, and in fact it's usually the case, that you have non-conservative internal forces. So the total energy of a system of particles does not remain conserved unless all these internal forces are conservative forces. So okay, that is all I wanted to say, and I think we are good for now to wrap this up. So I'll see you later.